Now, our next presenter is Jonathan McKinley, who is a graduate of the University of Waterloo and works at CanMet Materials on projects related to the deformation, forming, and performance of materials. He and others at CanMet Materials have been working with Transport Canada since 2015 on projects related to the testing and simulation of tank car materials. CanMet Materials is the largest research center in Canada dedicated to fabricating, processing, and evaluating metals and materials. Join me in welcoming Jonathan.
Thank you very much for that excellent introduction. Can everyone hear me?
Yep, looks good.
Okay, can everyone see my presentation?
Not at the moment.
That is...
Yep, that looks better.
Excellent. As stated, I am an engineer at CanMet Materials in Hamilton, and we have been working with Transport Canada for several years on evaluating the performance of tank car materials, typically targeting low temperatures and very high temperatures. The work that I wanted to present to you today is just a small snapshot of that work, and I'll be focusing on the performance of TC128B tank car welds from -80 degrees Celsius to 23 degrees Celsius. We looked at the chemical composition, the microstructure and the micro-hardness of this material, as well as tensile strength, failure location, and Charpy impact energy. And I just wanted to say that I've really enjoyed listening to all of these very large, broad presentations. And this is going to be the exact opposite of that, where we're talking about one very small piece of tank cars. So the material that we were testing is TC128B steel from an as-fabricated DOT-117 tank car that had been previously impact tested by the US Federal Railroad Administration. It was provided to us via Transport Canada from the FRA, and that was very helpful in doing these tests. We looked at some circumferential and longitudinal welds, as you can see in the pictures on the right. And we did many cross-weld tensile specimens and a few all-weld metal tests. There was a limit to the amount of testing that we could do on weld samples, which is why we used different types of samples. So on the right-hand side of the screen, you can see the macrographs of longitudinal and circumferential welds that we studied, and they show the typical attributes of a two-pass submerged arc weld. You can see the two weld regions, the heat affected zones, and a small amount of reheated weld metal in the first pass. We conducted Vickers micro-hardness tests across these welds through the center and 2 millimeters below the inside and outside surfaces. Micro-hardness is an excellent method for testing welds because there's always the potential for quite a bit of variability across a weld, given all of the complex microstructural things that are happening. And what this testing shows is that in all cases, the hardness through the weld was higher than that of the base metal, which was about 160 HV, and we did not see any significant numbers below that standard, which is exactly what we would like to see across a weld. This next slide, I show various locations of microstructure throughout the weld. Given the amount of time that I have for the presentation, I don't want to go into too much detail in all of these. There's lots more information in the paper and also the other reports that we've published on these topics. In general, I just wanted to mention that when you're looking inside of a weld, you can see many different types of microstructure, and it can vary quite substantially from fine-grained to coarse-grained, but also the structure can change from, generally homogeneous grains to a more complex grain structure. What we found when we were looking at the microstructure of these samples was that there was large quantities of coarse grain boundary ferrite in the center of the weld. There was some intergranular polygonal ferrite with a second phase and some acicular ferrite. Acicular ferrite is a very interesting type of microstructure where you have many interlocking platelets creating a very complex structure that has a tendency to be very tough and resilient. And I'll talk a little bit more about that later. So moving on to the tensile tests that we did, as I stated earlier, we did full all weld metal tests at room temperature. And these are shown on the left-hand side of your screen. The base metal in black and the longitudinal and circumferential tensile tests in red and green, respectively. You can see that the yield strength and the ultimate tensile strength of the welds are higher than the base metal. This is what we want and what we expect to see. We also see a slightly lower elongation to failure versus the base metal. Once again, all as expected. On the right-hand side of your screen, you can see the UTS compared to temperature of the cross-weld tensile specimens that we studied, ranging from -60 degrees up to 20 degrees Celsius. There's a few things to note. The first is that we don't take these as a measure of the weld strength because it's a sample that contains base metal and both weld, but it does show us whether or not the strength of the weld is at least as high as the base metal. What we like to see is the samples failing in the base metal rather than the weld, which is exactly what we saw in these samples. We also see the weld metal follows the same trend as the base metal, which is a reduction in tensile strength as the temperature increases. And even over this relatively small temperature range, there is quite a significant change in the strength of the material with temperature. So now on to the Charpy transition curves. And this is what I consider to be the most significant result that I'll be talking about today. So I will take some time here. So for those who may be unfamiliar, a Charpy test is a relatively simple, cost-effective test which measures the dynamic ability of a material to absorb energy. It is a great measure of how a material behaves in a crash or dynamic scenario, and it is a good indication of its resistance to cracking or fracturing in a brittle manner. So I'll start with the left-hand side of the screen, which shows a figure of the longitudinal material weld properties. The base metal is in black on the top, and you can see that as the temperature decreases, the Charpy impact toughness decreases as expected. The circumferential heat affected zone is in green below that curve, and then way down below that is the curve for the circumferential weld metal. So the impact energy, the CVN number for the weld is substantially lower than that of the base material. The trend for the longitudinal welds is generally similar to that of the circumferential weld. The weld curve in red at the bottom is substantially lower than that of the base metal and the heat affected zone. So in this case, the heat affected zone was actually above the base material. So moving on, the next curve shows both the longitudinal and circumferential welds on the same figure, so we can compare them together. You'll see that the longitudinal weld that had 40% acicular ferrite had a significantly higher Charpy impact energy at most temperatures than the circumferential welds with 25%. So we think one major contributor to the performance of these welds was the amount of acicular ferrite that was present. And I've sort of mentioned two things in these curves. One is that the trend is not uncommon. It's standard trend for temperature and welds, but we are seeing a substantially lower Charpy impact energy for the welds than the base material. In this next slide, I am showing the fracture surfaces of two of our tensile tests at different temperatures, and both have two different levels of magnification, lower level of magnification on the top, higher level of magnification on the bottom. On the left-hand side, you can see ductile fracture at 25 degrees Celsius, and on the right-hand side, you can see brittle cleavage fracture at negative 46 degrees Celsius. The left-hand side, ductile, absorbed 69 joules of energy, while on the right-hand side, it was 13 joules of energy. So there's, between the extreme ranges that you might expect this material to perform in, there is a vast difference in how it may actually perform in practice. When you look at the lower images, you can see that there's these ductile voids forming at 25 degrees Celsius versus a completely different brittle fracture surface at negative 46 degrees Celsius. So moving on, the conclusions from these tests were that the Charpy impact energy of the weld metal was significantly lower than that of the base metal. The particularly low CVN of the circumferential weld may be due to high carbon and oxygen content and coarse pro-eutectite ferrite, which, given the time I didn't spend much time on, I concentrated on the acicular ferrite, which we think is the leading cause. During an accident involving an impact such as hard coupling or derailment, the weld is more likely to fail due to low toughness. Improving the toughness of the weld metal would reduce the chance of fracture rupture under all service conditions. Weld toughness can be improved by adjusting the welding parameters, the filler metal, or reducing the heat or current supplied to the weld, potentially adding or changing the shielding and the post-weld heat treatment. So moves me on to why we wanted to present this today. As I said, these results are not unexpected, but we do think that the performance of the weld is lower than what might be achievable with some very small changes. And it also is an indication of the kinds of things that you might want to track or inspect when you're looking at rail infrastructure as a whole. We thought that the results were interesting enough that we wanted to make sure that we got this data out there for those in the rail industry to look at and be aware of. And lastly, I would like to thank Transport Canada, particularly the Transportation of Dangerous Goods Directorate, for supporting and funding this work. And I would like to thank Ian Whittle and Henry Liu at Transport Canada for being involved and helping us with this project. All right, thank you very much.
Thanks so much for that interesting presentation, Jonathan.